Alright, so today we'll work with Bernoulli differential equations, and I'm abbreviating differential equations using the letters DE. So if you hear me say DE, I mean a differential equation. Now, first thing is to start with a standard form. So a Bernoulli equation has a standard form, which is slightly similar to the standard form of a first order linear differential equation. So it goes y prime plus some function p of t times y equals some other function g of t times y raised to the power n. Now here again I'm treating t as the independent variable and y as the dependent variable, which is at this point an unknown function of t, and the goal is to find the function y which satisfies this differential equation. So as you can notice, this is almost like the standard form of a first order linear differential equation. The only difference here is that the right hand side, the g of t, is multiplied with y to the power of n, where n is allowed to be any real number. So for the choice of n, if n is 0 or 1, then the equation reduces down to a linear, and that is not our interest here. So we will assume that n is some number so that it makes this differential equation non-linear. The goal of solving these kinds of problems is to make these equations linear and then use the methods we know to solve a first order linear differential equation. So we introduce an appropriate change of variables. And again, I'm going to abbreviate change of variables using the letters COV. It stands for change of variables. So the change of variables, let's suppose we can make some new variable v, which is y raised to the power k, for some number k, which let's suppose we do not know right now. So remember, y is a function of t, y to the k is now a function of y, which is a function of t. And so v is also a function of t. So we can differentiate v with respect to t. So if I use the prime notation, I'm going to say v prime. So v prime here is the derivative of v with respect to t. And so if we differentiate both the sides, on the right hand side we can simply apply the power rule for differentiation, and we get k times y raised to k minus 1. However, because y is some unknown function of t, by the chain rule we have to multiply this by y prime. And so if we solve for y prime, we get y prime equals v prime divided by k times y raised to k minus 1. So let's make this substitution into the standard form that we have up above. So I will again start with the standard form, but this time I will use a new color for y prime. So let's say that we have y prime plus p of t times y equals g of t times y raised to n. So we will replace y prime with this form that we have for v. So this becomes v prime divided by k times y raised to k minus 1. And then we will keep the remaining equation as it is. So followed by plus p of t y equals g of t times y raised to the power n. So at this point, our goal is to eliminate this fraction with v prime. So we want to cancel out the denominator k times y raised to k minus 1, which we can easily do by multiplying everything by the denominator of v prime. So if we multiply this throughout with k times y raised to k minus 1, we have v prime plus p of t times k times y raised to k minus 1 times y, and that equals g of t times k times y raised to k minus 1 times y raised to n. Now notice here that I'm multiplying this denominator in between p of t and y, because in multiplying terms together we can swap the order of multiplication. So I could have multiplied this in the front of p of t, or after this y, or in between p of t and y. So either way. Okay, so let's simplify this. Therefore, we have v prime. Let me bring this constant k in the front. So we have k times p of t. Now we can combine the two y's because they have the same base and different exponents, so we can add the exponents. So if you add the exponents, you have k minus 1 plus 1, which comes out to a k. And that is equal to, again, let's bring this k in the front, and we have y raised to k minus 1 plus n. Now, one thing to notice here is this y raised to k. So if you recall, this was our initial substitution up here, which is v. So I can replace this y raised to k with a v. And so therefore, we have v prime plus k times p of t times v equals k times y raised to k minus 1 plus n. So at this point, it doesn't look any easier than this form we started with. But remember, we still have not said what k should be. So we have the freedom to choose the value of k so that this equation becomes linear. And the only option that we have left for the value of k is 1 minus n. And how do we get that result? Well, that is because if you notice on the right hand side, this is the only term we need to eliminate in order to make this equation linear. So we can eliminate this term if the exponent of y is a 0. And so if we let k minus 1 plus n equal 0 and solve for k, we get k equals 1 minus n. And now, if we substitute this 1 minus n back into this equation, the most recent one we have written, it becomes v prime plus k can be replaced by 1 minus n, p of t times v equals, again, the k on the right hand side can be replaced by 1 minus n, g of t. I believe we have to carry down the g of t on to the right. And that is it. So this is now a first order linear differential equation. So in conclusion, the substitution we want to make is v equals y raised to 1 minus n, and then we differentiate and make the substitution in the given equation, and it will become always a linear first order differential equation. And then we may solve this using the methods we know, either by using the techniques of a separable equation, that is, if the resulting equation is separable, and if it's not, then we can use the method of integrating factor.